In today's video, we're still going to be talking about section 3.4. So we're going to be dealing with velocity and other rates of change. And this is largely going to be a review of what we've been doing the last couple of days and getting into a little greater depth in terms of analyzing the motion of a particle. So we're going to be using all the same ideas we have been, but just kind of summarizing and making sure we're really clear when we read a question about what's being asked. So for this first part, this whole first page on page 55, we're given the position function for a particle that's traveling along a line, and it's a pretty basic polynomial function, so it'll be nice and easy to differentiate when that time comes. And we're told that the position is measured in meters and the time is measured in seconds. Okay, so the first thing they're asking us to do is find the displacement of the particle during the first 2 seconds. So our key here is displacement. And when we see displacement, what this is really asking is for the change in position. That's what we need to find when we're asked to find the displacement. So we know that our position function is our function s of t. And so if I'm finding the displacement over the first 2 seconds, I know I need to find the position at time 2 seconds, and I'm going to subtract the position at time t equals 0 seconds. And so this is just plugging directly into that position function. So I know I'm going to kind of set this off to the side. S of 2 is going to be 2 cubed minus 18 times 2 squared plus 81 times 2. And I'm just going to use my calculator to figure that out quickly. And if I calculated that correctly, which I'm sure you'll let me know if I didn't, S of 2 is 98. S of 0 is going to be a lot easier to figure out. Since I have no constant terms here, my S of 0 is just 0. So my displacement then over those 2 seconds is 98, and I know my units are meters. So that means my object is 98 meters to the right of where it started. So the next part asks me to find the average velocity. Okay, and like we've been talking about, average velocity, what it's really asking me to find is the slope of the position function. So in other words, I need to find the change in position over the change in time. So to calculate this average velocity, we need to find, I'm doing this over the first 4 seconds, so I have S of 4 minus S of 0 over 4 minus 0. So again, let's see, let's calculate this. Looks like S of 4 is 100. S of 0 is still 0 over 4. So I get 25, and my units, we know this is a rate of change here, so my units are meters per second. So average velocity is just our slope formula. Now we get into the part we're going to start using our derivatives. So when I see instantaneous velocity, hopefully, again, we talked about this a little bit in class today, but when I see instantaneous velocity, I should be thinking the derivative. So to find that instantaneous velocity, I'm really asking to find that derivative of the position function. That's going to give me the instantaneous velocity. So the first thing I'm going to do is just find my general velocity formula, which I know is the first derivative of position. And for this function, we're going to have 3t squared, basic power rule, minus 36t plus 81. So now I want to find that at the instant when t equals 4. So I'm going to calculate this when t is 4. And it looks like I get negative 15. So since that velocity is negative, I know that I'm moving to the left at that point in time. And again, I have a rate here, so my units are meters per second. Okay, moving right along. Part D wants me to find the acceleration. Now, when I'm finding acceleration, I know I'm going to find that by taking the derivative of my velocity function. So a of t is the first derivative of v of t, or my velocity function. So I'm just going to go take my velocity function again and use the power rule. So I have 6t minus 36. And so I can evaluate that when t equals 4. And I get a negative 12. And now we have units of meters per second squared. Okay, and so the last part for this problem now, we want to know at what value of t does the particle change directions? Okay, and I know that this happens when velocity is equal to 0. So this is asking us to find when v of t is equal to 0. So we're going back to our velocity function here. So v of t is equal to 3t squared minus 36t plus 81. And I want to find when that's equal to 0. So I'm going to go ahead and factor out a 3 and then hope that this factors nicely for me. Okay, and it looks like right away I see that if I multiply 9 times 3, those are going to allow me to add up to this negative 12. So I'm going to try t minus 3 and t minus 9. And so that'll get me factored correctly, so then I know that I'm changing directions at t equals 3 and 9 seconds. Okay, so those are some basic things that we need to be able to compute relative to these particle motion problems. So on the next page, we're going to do the same thing. It's a little less scaffolded, so a little less prompting. And we're going to look a little more into not only when is it changing directions, but when is it going right and left, and when is it speeding up and slowing down. All right, so let's go ahead and turn the page and see what we got. Okay, so this would be kind of like a level 2 type problem. So again, getting a little deeper into analyzing this particle motion. So again, we're still given the position function here. Okay, and then we're asked to find all of these different things. And a lot of it is going to follow just what we did on the previous page. So again, for part A, displacement means I want to find the change in position between time equals 10 and 12 seconds. So we're just simply going to calculate s of 12 minus s of 10. That has strictly to do with the position. So hopefully you guys are double checking my calculations here. Well, hopefully I get them right, but hopefully you're also double checking me. Looks like s of 12 I get negative 6. And for s of 10, I get negative 4. So here we have to be a little bit careful. We have a negative 6 minus a negative 4, which we know is going to be positive. So I get a negative 2 meters. And again, what that's telling us is that the object ended up 2 meters to the left of where it started. Okay, average velocity. And the nice thing is here I'm using the same interval, so I don't have to recalculate some of these values. We know the average velocity is just the slope of my position function. So my change in position, s of 12 minus s of 10, over the change in time, which is 12 minus 10. So since I have the same interval, I'm not going to recalculate this, assuming I did it correctly. I know my change in position is -2. My change in time is 2. So my average velocity is -1 meters per second. Okay, so now is where I get into my derivative with my instantaneous velocity. That tells me I need a derivative. So the first thing I need to do is calculate or figure out here my velocity function. Again, that's the first derivative of position. So I have 2t minus 23, a nice easy function to work with. And I'm going to find my velocity at t equals 4. Whoop. And I get -15 meters per second. Now, speed we haven't gotten into too much, but if we remember back to the previous video, speed is just the absolute value of velocity, because speed is only concerned with how fast the particle is moving, not the direction. So if I want to find the speed, I need the absolute value of the velocity when time equals 4, which I know from this result here is the absolute value of -15. So my speed is just 15 meters per second. Again, we don't take into account the direction of travel when we're talking about speed. All right, so let's keep moving here. Part E, when does the acceleration of the particle equal 0? So now this is a little more involved. It's not just asking us for the acceleration at a certain time. We need to solve for the time when the acceleration is 0. So first we need to figure out our acceleration function. We know that it's the first derivative of velocity. And so if I look back to my velocity function, I have 2t minus 23. So my derivative is going to be 2. So I know I have a constant acceleration of 2 meters per second squared. So that tells me that in this case, the acceleration is never equal to 0. Because we have a constant acceleration of 2 meters per second squared. All right, so now is where we're going to start pulling together some of this from what we know of velocity and acceleration. So here, when does the particle change directions? We know that happens wherever the velocity is equal to 0. So again, we're back to that velocity function, which is 2t minus 23, and we want to know when that's equal to 0. So we're just going to go ahead and solve this simple linear equation. And I know that happens at t equals 11.5 seconds. So that's when I'm changing directions. And for a minute, instead of going on to G, I'm going to go down to H here, because that's going to be directly using the information we found in Part F. So when the particle is moving to the right, I know that velocity is greater than 0. And for the left, I know that happens when the velocity is less than 0. So just like we did in class today, or actually not today, we've done it a couple days ago now, I'm going to make a little number line to help organize what's happening here. And so I have my velocity, and I know that it's 0, that my object is changing direction at t equals 11.5 seconds. So now I'm going to pick a value that's less than 11.5 and a value that's greater than 11.5 to figure out the signs of those values. So I'm, for instance, might pick 10. And so into my velocity function here, I'm going to plug in 10. And if I do that, I notice I get a negative value for velocity. And similarly, I'm going to pick a value larger than 11.5, say 12. If I plug that into my velocity function, I get a positive value. So what this is telling me is that the particle is moving to the right for time between 0 and 11.5 seconds. Excuse me, that's not true. The particle is moving to the left on that interval because my velocity is less than 0. Now I'm moving right for time greater than 11.5 because my velocity is greater than 0. Oops, let me scoot this up. Sorry about that. Oh my goodness. Here we go. Because velocity is greater than 0. So now the last piece of this we want to consider is when the particle is speeding up and when it's slowing down. We know it's speeding up when v of t, velocity, and acceleration have the same sign. And I'm slowing down when those two functions have opposite signs. So I'm going to use my number line again to help me organize my information. So I'm just going to copy what I had over here. And so same thing, I knew 11.5 was an important point for figuring out the signs of velocity. So it was negative to the left and positive to the right. And now I'm going to add another row for my acceleration. Now, we already set up here that we had a constant acceleration of positive 2. So that means over my whole interval, my acceleration is always positive. So now I can see on this interval, velocity and acceleration have opposite signs. So I know I'm slowing down on that interval. So the particle is slowing down on the interval from 0 to 11.5. And because velocity and acceleration are both positive, on this interval, they have the same sign. I know I'm speeding up. For my time greater than 11.5. Okay, so that's the type of analysis we'll be doing. We'll work on another group example when we get to class tomorrow, and then you'll have some time to work with this and kind of sort out any issues you're still having. See you tomorrow.